And welcome everyone once again to another Waterloo Wellington First workshop for the Iligu competition. Tonight's workshop is on 3D printers. It's a very early introduction for people who don't know anything at all about 3D printing. We will be having more of these 3D printing workshops in the next few days, and they'll provide a lot more details. Tonight's presentation is by Tyler. He is a student on the 2702 Rebels. And if Tyler, you could start sharing your screen, I will turn it over to you.
All right. So yeah, my name is Tyler. Then done a lot of playing with 3D printers. So they're just gonna start just to establish a baseline so that everyone knows what I'm talking about when I say things later on. Okay, so the plan for this, start with the introduction, again, establish a baseline, then we'll move on to setting up, selecting a printer, setting up what it takes to set one up, as well as using a slicer. Then we'll move on to making printing parts for strength. So that'll be impact resistance and heat resistance, that kind of stuff. The fourth one will be bed adhesion and leveling, because that is the most fun and the most common problems. And then 5 will be some common failures, as well as some more resources if you ever have any problems with, or you just want to learn more in general. So today's overview, we're going to talk about the Rebels history with 3D printing. My experiences, I'm going to use the 2017 bot to show how 3D printing can be used at scale. We're going to talk about what SLA printing is and what FDM printing is. And then I'm going to talk about the printer anatomy for an FDM machine, the Hotend breakdown for an FDM machine, and then some interesting applications. So the Rebels started printing, 3D print has been 3D printing since 2014. During that year, we had some significant issues with 3D printed parts. After this experience, we reevaluated our strategy for 3D printing and used it successfully for consecutive years. Over the past 5 years, we've won 4 awards for our use of 3D printing. I guess that'll be 6 now. The last year being 2019, 3D printing enabled our team. I guess every year it's really 3D printing enabled our team to compete. Our strategy that ended up winning us the creativity award on our field at provincials. So again, that is 2019, not 2020, because obviously no one got that far. So this is the 2017 bot. So you can see on the left, you can see if the CAD model with all the non-printed parts suppressed, and on the right you can see the completed robot. So not everything is printed in blue, but you can see some of the white parts, all the blue parts, obviously, and those black spools on the back are all 3D printed. So this kind of shows that it's not only at a small scale that you can use it. Yeah, so you can use it at quite a large scale if you have enough 3D printers or a printer that's capable of printing a lot of objects at the same time. So some of the stuff I've learned, I started with a Dremel 3D20 that I got on loan from my dad's work. I learned the importance of a heated bed and the hacks to getting around not having one. I then was able to get a hold of a Replicator 2X, also from my dad's work, which taught me some lessons with ABS filament loading and the struggle that can be leveling. And then in 2019, I went out and bought a Prusa Mark III, which taught me how to build a printer, the very expensive lesson in silicone socks, printing PETG, and the importance of having spare parts for your printer. And then over the summer, I spent a good chunk of my summer building the Open RCF1 car you can see in the bottom right there. That taught me a lot more about impact resistance as well as shear force. I learned a lot because the only part that might be original on that car are the wheels. Everything else has been broken at least once. In the case of the front wing, many, many times. All right, so let's start with what is SLA, because that won't be the focus. So it's stereolithography. It cures layer by layer, just like an FDM machine. It uses a LCD screen using UV light to cure thin layers of liquid plastic. That process is called photopolymerization. Some notable examples of companies that make these type of machines are Formlabs, that's their specialty, the Prusa SL1, and the Elegoo Mars. So Formlabs being the most expensive is about $2,000, and Elegoo Mars being $300-ish, which is very cheap to play with it and get some experience with it before you buy something a little more expensive. So the requirements for good ventilation, a curing station, or a place to cure like a window, because the parts don't actually come out completely solid. They come out mostly solid and then cure the remaining in either a curing station, which is always sold separate, which is usually, if not always, sold separately. Or if you place it in a window, the UV rays from the sun will cure the remainder of the part. You also need a lot of IPA for washing it. IPA is isopropyl alcohol. It's pretty helpful to have for quite a few different 3D printers, as well as obviously this one for cleaning the parts, because they actually still come out with the liquid resin, which will probably stain your skin, and it's definitely not good for you to touch without gloves. So you should also have gloves if you're dealing with an SLA machine. All right, so what is FDM? This will be the focus, because this is what I've spent the most time on. So FDM is fused deposition modeling, or FFF, fused filament fabrication. They're kind of used interchangeably. Some common makes are Creality, MakerBot, and Prusa. You've probably seen the Creality ones. Those are the Ender 3s and the CR10s. And then they're generally much more expensive because the Prusa i3s. So the best way that I can try to explain it is FDM is basically, it's like a hot glue gun that moves around on the build plate. So it squeezes out, instead of glue, it's plastic, and it moves, pushes out some more plastic, moves a little bit more. So I got this graphic here that hopefully should make it easier. So you start with the 3D model, in this case a skull. You put that, you then place that in a slicer, which will cut it into layers that can then print. And then you put that in your printer, and then your printer will pull the spool of plastic off the spool through the extruder gears, which are used to push the filament into the hot end. Think of like the spring mechanism on a hot glue gun, which then pushes it out the hot end like the nozzle of a hot glue gun. Yeah. And then one thing that makes 3D printing super, super nice is that most, if not all, parts are printed to some degree of hollow. So you can kind of see in the graphic right there that that's got those blue lines. Those blue lines are still plastic, but they form what's called infill. In this case, it looks like it's rectilinear. And then it uses that to still reinforce the strength of the part without having to use all solid plastic, which is much more expensive and takes a lot longer. Yeah. Yeah, so a spool of filament goes actually quite a long way. Usually you can buy them in about a kilogram for anywhere. If you're really on the ball, you can get some for as cheap as $15, upwards to like $55 a spool, which is a little bit more pricey, and it's not necessarily you get what you pay for. There's some really good filament that costs not a lot of money, and there's some really expensive filament that is really bad. You just do your research. It's like anything else. So let's talk about the anatomy of an FDM printer. So I've got a picture of my Prusa here. So that that black frame obviously is the frame. It holds everything together. Not really super complicated. Then you've got the x-axis, which moves left and right, as well as the y-axis, which moves front to back. Some printers will actually have the extruder, which you can see labeled there on two different, on the same, not the same. The build plate doesn't move, it only moves up and down, and the extruder will move left and right and forward and back on its own. This one doesn't. A lot of the Cartesian style machines, which is what the Prusa is, as well as the most common Creality printers. An example of one that moves the Hotend forward and backwards and left and right at the same height is the MakerBot replicator line. That's how those ones move, though. Although it all transfers. It's not a whole lot different, just changing if the bed or the Hotend is moving in a particular axis. And then you obviously got the Z-axis, which moves up and down. So that not super complicated. The extruder, some companies call it the E-axis. So if you see E-axis, it's just the extruder. They've just chosen to name it something different. So most extruders you can see have a fan on them. That's just to keep them from getting too hot, because these things get very, very warm. Like some of them go upwards of 300 degrees Celsius, which I'll talk about how they avoid doing that all the time a little bit later. And then you got the build plate, which is probably the second most important part of the printer, only behind the extruder. The build plate allows you to actually print something. It generally has to be leveled in some way. There's printers like the Prusas that do it differently, and the bed doesn't get leveled. The nozzle gets calibrated for a height. But most of them you have to level. It's super important to get that right, or else your prints won't work. There are also multiple different types of build plates. So I have a metal one, but glass ones exist, as well as they're like a I don't know how to describe it, but they're like a plastic, but they're what's it called? Like Lexan, I think. Not totally sure off the top of my head. And then they'll have some layer of something that will it'll allow parts to stick to the otherwise slick surface. So to take an overview of an FDM Hotend. So from the outside, so this is what you'd be able to see if you pulled one off the printer. Obviously, the big part of it is the heat sink. That just prevents the filament from getting too hot too early, which will actually cause most Hotends to jam, which means your print fails and you have to start again. Then you've got the second biggest piece, the heater block. That's that big rectangle. That holds the heater cartridge as well as the thermistor and the nozzle. So the heater, obviously, it just heats that. The heater block, obviously. The thermistor measures the temperature of the heat block, and it's there to regulate the temperature so that it doesn't get too hot or get too cold. So it doesn't, in some extreme cases, set something on fire, or if it gets too cold, have the plastic not melt enough in the Hotend and cause a jam. The nozzle, which you can kind of see there on the end, that just pushes out that's where the filament gets pushed out of. It's usually a different diameter than the diameter of the filament you actually put in the in it, so that in the printers, so that it can print with more accuracy. So this is what you'd see if you were to take well, specifically, this is an E3D V6. They'll all be very similar though. So if you were to take one and cut it in half, this is what you would see. So you would see, again, the heater cartridge. New part that you can now see is the heat break. That's that part in red. It's just a spot that gets a little bit warmer, so the plastic can start to melt before it hits the nozzle. If you push too much filament through, that has to get a lot warmer so that you don't get a jam. You can kind of see it's kind of cut off in the picture that the nozzle just kind of changes the filament diameter so that it prints properly and prints well. Okay, so 1 second. I am missing some slides. 1 second here. Okay, very strange. I'm not sure those slides went. So some interesting applications, some pulleys and gears. So this is some examples of things that you either need done custom or can simply just done quickly, or and in the case of FRC, it's cheaper, which helps with your budget. It allows you can print pulleys and gears, which are great with various shafts and tooth counts. So they're perfect for grippers. So that red one on the right there, I believe, if I remember correctly, that would be off of our 2018 second cube mechanism. And then on the right, I've just got the drive gears from my open RC car. They're actually surprisingly strong, and the only time I've ever actually destroyed a 3D printed gear while in use is when I put the brakes on my car too hard. But that takes quite a lot of force to actually strip anything. So it never hurts to have a spare on hand, but I wouldn't be too concerned about them stripping unless you're going to use them for something like driving your robot, at which point properly manufactured gears and pulleys would probably be the way to go. And then some interesting applications. We actually made our intake, the Mecanum wheels on our intake from our 2020 bot. We printed all the Mecanum wheels. They originally just printed for prototyping, but ordering the wheels was going to be expensive and slow. So we just ended up printing them. And this actually kind of shows why 3D printing is so super handy for this kind of stuff. Like, not only is the material most of the time quite a bit cheaper, but if you play with it, you can often get a good quality result that is very similar. So it's like these wheels, I believe I'm not totally sure if they're lighter. I don't remember what the number was, but they worked. We were able to print as many of them as we needed. And if the design changed, we could print more. We could make changes if we had to. So that's pretty much it for an introduction and establishing a baseline for 3D printing. The next one will be talking about how you pick a printer, as well as getting one set up, as well as a slicer tutorial. So that'll be using a slicer. I'm going to use Cura and Prusa Slicer because those are the ones I'm most familiar with. All right, any questions? Yeah, so Terry says here, and I just totally slipped my mind. Common build surfaces PEI, that's actually what's on my metal build plate. That's also actually on those Lexan-like build plates. Some people also use a thing called build tack. I've never used it, but I've heard it's good. Yeah, so one of the really handy things about PEI is that it actually, ABS and PLA stick to it really well when it's warm. But as soon as it cools down, it releases, which means you don't need to scrape your prints off the bed. which can be a little bit dangerous at times. So wear some gloves if you can, or yeah, generally just try to wear some gloves, or at least don't put your hand somewhere where you might cut yourself.